Good morning, Abstract Algebra. This is our last live streaming session of the spring semester 2019. Before we get started, I just want to say that I'm so glad to have been able to do these with you this semester. I think it's been a really valuable opportunity for us not only to interact a little bit more outside of the classroom, but also to get some more chances to get exposure to the kinds of problem solving that we do in abstract algebra, get a little bit more, build out our repertoire of techniques and tools. So this last session for the semester is going to focus on topics that are most germane to preparing for the final exam, which comes up tomorrow. And based on the feedback and the input that you've given me over Slack, which again, if you're watching this live, feel free to interact via Slack, ask questions, ask for clarification, and so forth. I'll respond to those in real time. What I heard from you is that the topics that you're most interested in hearing more about, and this is not a surprise because these are the last ones in the semester and we didn't get a lot of time for them to sink in yet, are related to the topics of normal subgroups and factor groups and homomorphisms. So in the numbering scheme of our course, these are topics 7, 9, and 10. And I'm going to also sort of tag in here a topic that is way back from chapter 3, because what I want to do in the course of today's session is kind of compare and contrast between two notions of commuting within a group that at a glance seem very similar, and there is in fact a relation between the two of them, but it's also easy to confuse them with one another and be led astray. And those two notions are the notion of the center of a group and the notion of a normal subgroup. And what I saw on a few of your works on quizzes and exams is that when it comes to actually using the definition of a normal subgroup, some of you were trying to think instead about the definition of the center of a group. And so hopefully we'll understand in a minute why that's the case. So I want to contrast very clearly between those notions. Then I want to look at a couple of examples of factor groups that are maybe factor groups that you've seen in disguise in your past. Some factor groups of which we've seen in disguise this semester in abstract algebra, and others that you may be familiar with from elsewhere in your mathematics life, in your math education. So I want to look at a couple examples of cosets and factor groups, both in the additive group of the integers and also in the additive group of the real numbers. And then I want to kind of try and sew some things together by bringing back that idea of center of a group, and using the center as an example of a normal subgroup. There's a theorem that we didn't spend a lot of time on, but I think it's kind of a nifty thing for us to think about now, so that again it gives us the opportunity to dwell in these definitions a little bit, that I call the nifty center theorem. It's otherwise called the G mod Z theorem elsewhere in the literature. And what it does is it sort of constrains what the center of a group may be. It can't just be any old normal subgroup. The quotient of a group by its center tells us something important about, in fact, the whole group. So we'll see what that looks like in what I call the nifty center theorem. And then hopefully we'll also have time to do a quick homomorphism counting problem. These are the kinds of problems that come up frequently in standard number 10, because this really, what it amounts to is it amounts to us thinking carefully about the subgroups of both the domain and the target group for a homomorphism, and figure out which ones of the normal subgroups of the domain may be the kernel of that homomorphism, and which one of the any subgroups of the target group may be the image of that homomorphism. And very often, just by counting the orders of those subgroups, if we know them all, we can come up with the right set of constraints on what kinds of homomorphisms can even exist between a pair of two groups. So the theme, the title of today's final exam review is The Center Cannot Hold. And so what I want to do is start by thinking about the contrast in definitions between the center of a group and a normal subgroup. So we'll start by picking just an arbitrary group G. I'll pick an element, little g, that belongs to my group, and I'll also pick a subgroup, capital H, of collection of elements that belongs to G, which itself satisfies identity, closure, and inverse properties. And so here's the difference. Here's the reason why it's easy to confuse the idea of center and the idea of normal subgroup. Because in both cases, we're sort of saying the same thing. If I'm an element, little g, and I belong to the center of this group, then what that means is that every element of the group G commutes with me, right? I can be put on either side of any element at all that I choose from my group, And that product is going to be the same either way if I, G, belong to the center of the group. And then meanwhile, H, my subgroup, can say that it is a normal subgroup in G if, as a set of elements, it commutes with everything in my group. So in both cases, G and H are saying the same thing. Everything commutes with me. But the problem is that when an element says that sentence, it carries a very different and more specific meaning with it than if a whole set says that phrase. If an element is able to say everything commutes with me, then that element by definition belongs to the center of the group G. Right? The center being the set of all elements of G such that for all other elements of G, all those elements commute with my element. So if X belongs to the center, then X commutes with Y for all elements Y in my group. So G belongs to the center. G is playing the role of this X, right? GY is equal to YG for all elements Y that I take from my group. On the other hand, if I'm a normal subgroup, that means that I'm a subgroup that's capable of saying everything commutes with me. And again, it looks very similar. For all elements of my group, that element times my subgroup on the left agrees with that element times my subgroup on the right. So these notions look very similar on their face, and they both have to do with commuting. Right? And so for that reason, there's an important relationship between the two of these things. In particular, we can always say that the center of a group is always a normal subgroup of G. Right? So if you can tell me what the center of a group is, then you have given me an example of a normal subgroup. And for that reason, any subgroup of the center is also a normal subgroup. So not even necessarily just the whole center. If I have any subgroup of the center, that subgroup will also be a normal subgroup of the group G. Unfortunately, it doesn't go the other way. So the center of a group is always normal. But not every normal subgroup is a subgroup of the center. So central implies normal, but normal does not necessarily imply central. So what I want to do is I want to look at an example that will really, I hope, to help to cement the difference between these definitions. So let's start with a dihedral group of the dodecagon, the dihedral group of order 24. It's the symmetries of the dodecagon. And I'm going to take the subgroup that consists of the identity and the third, sixth, and ninth powers of the generating rotation for this dihedral group. So these would be, if R is rotation by 30 degrees, then that would mean I would have here a 90-degree rotation, a 180-degree rotation, and a 270-degree rotation, and the identity. So that's my subgroup. You can verify that this is in fact a subgroup for the dihedral group of the dodecagon. And so I want to ask two similar questions. Pick an element from D12. I'm going to pick the reflection, whatever standard reflection that we fix across an axis of symmetry of that dodecagon. Does that reflection commute with every element of my subgroup? And separate question, does that reflection commute with the set H? And if you grasp the difference between these two questions, then you're grasping the difference between center and normal subgroup. Right? So, okay, let's try and answer each of these questions. And to do that, I'm going to kind of go back to the sort of rows by columns picture that I tend to fall back on a lot in these conversations. So in a row here, I'm going to list the elements of my subgroup. Call it H. My elements are I, R to the third, R to the sixth, and R to the ninth. So if I want to know whether T commutes with every element of H, then what I want to do is take every element of H and just multiply it on the left by T, and then also multiply it on the right by T. So suppose I take R to the, well, why don't I take R to the sixth, just to get started, right? If I multiply on the left by T, then the result of that product is going to be TR to the sixth. On the other hand, if I multiply on the right by T, then the result is R to the sixth times T. Okay. And what happens now in this situation? Well, now we have to remember how the dihedral group works, right? What the relation is in the dihedral group between T's and R's. Because T and R don't generally commute in the dihedral group. But we have a nice relation in the dihedral group that tells me how I can move all the T's to the left sides of the R's. Remember, in any dihedral group, RT, if I have a T that's on the right side of an R, I can move it to the left side instead at the cost of inverting that R. Right? So this is the dihedral group, one of the dihedral group relations. That's what makes it dihedral. And so what that allows me to do is leapfrog this T to the left side of all 6 of these R's. And every R that I leap past is going to trade into its own inverse. So R to the 6 times T ends up being the same thing as T times R to the minus 6. But what is R to the minus 6 in the dihedral group of the dodecagon? Because R to the 12th is equal to the identity, R is an element of order 12. That means, multiplying both sides of this relation by R to the minus 6, it means that R to the 6th is the same as R to the minus 6. And the way to see that, thinking about symmetries of a dodecagon, R to the 6th is a 180-degree rotation. So it's just taking, I don't have an object handy. Let me use this spoon that I just used to eat my cereal. This is why I like doing live streams at home. So 180-degree rotation of this spoon, counterclockwise, is going to end up in this position. What's the inverse of that? It would be a rotation of this spoon 180 degrees clockwise instead. But that's exactly the same symmetry, right? 180-degree clockwise rotation is the same as 180-degree counterclockwise rotation as far as the final result of that rotation, right? And so TR to the minus 6 is really in the dihedral group the same thing as TR to the 6th. And so after all of that arithmetic, what we find out is that right multiplication by T and left multiplication by T both end up being the same operation when I'm multiplying by R to the 6th. TR to the 6th is equal to R to the 6th times T. They both end up in the same element of the dihedral group of the dodecagon. All right, but that's just one element. Right? Remember, the question that I posed here is it true for all elements of H that T commutes with every element of H? So we got to keep going. Let's try left multiplying R cubed by T. If I left multiply R cubed by T, I'm going to end up with the element that we call TR cubed. And then why don't we also left multiply R to the 9th? I get TR to the 9th. And if I left multiply the identity, I get the element T. And so what we've just built here, these 4 elements are a left coset of H. Right? They're the left coset TH. Whoops. Right. So does T commute with every element of H? Well, T commutes with R to the 6th. Does it commute with R to the 3rd? So to figure that out, I'm just going to multiply R to the 3rd on the right by T. I'm going to get R to the 3rd times T. If I do that with R to the 9th, I get R to the 9th times T. If I do that with the identity element, I'm going to get identity times T, which again, because of the two-sided identity property, just gives me T. And in so doing, I've constructed a right coset, the right coset that we call HT. Right? All right, so if I were with all of you in a classroom right now, I would ask you, what do you notice and what do you wonder about what's just happened here? We multiplied every element of this subgroup H on the right by T, and we also multiplied every element on the left by T. And it turned out that T commuted with R to the 6th, because the element, exactly the element that I got both of those times, was exactly the same. TR to the 6th and R to the 6th T are equal in the dihedral group D12. But what's R to the 3rd times T? If I simplify that, let me give myself some room to do that just over my head here. R to the 3rd times T. Well, what I need to do is I need to take this T right here, and I need to leapfrog it to the left side of 3 powers of R. And every time I do that, this dihedral group relation right here is going to turn those R's into R inverses. So this is T R to the minus 3. But again, remembering that the order of r in the dihedral group of the dodecagon is 12, r to the minus 3 is the same thing as r to any power which is congruent to minus 3 mod 12. So for example, r to the ninth. T to the minus 3 is the same as tr to the ninth because minus 3 and 9 are congruent mod 12, which is the order of r. Right? And so this element here in my right coset that I get by multiplying on the right r cubed times t is actually tr to the ninth. And for the same reason, when I do r to the ninth times t, and I leapfrog that t past all 9 powers of that r, it makes all 9 of those r's negative powers, inverses. And then when this 9 minus 9 right here is congruent to a positive 3 mod 12, we find out that this element of the right coset is really tr to the power 3. So now I've done all of the dihedral group simplification that is fit to do here. So I'm looking at every one of these elements with the t's coming first and the r's coming second, so we have a level playing field to understand which elements are really equal to which other elements in these cosets. So let's revisit our question. First of all, does t commute with every element of H? And the answer is no. T does not commute with every element of H. It in fact commutes with 2 of them, but it doesn't commute with the other 2. So notice T commutes with I, right, the identity. After all, the identity commutes with everything because it's a 2-sided identity. So I times T gives me the same element as T times I. Right? T also commutes with r to the 6th. Right? T times r to the 6th gives me the same element of the dihedral group as r to the 6th times T. So let's spell that out here. It commutes with I and with r to the 6th, but not with the other 2 elements, because t times r to the 3rd is not the same element as r to the 3rd times t. So just to drive home my point here, I'll highlight. That's the discrepancy that I'm looking at here, right? An element by element discrepancy. tr to the 9th is not the same thing as tr to the 3rd, right? And therefore, t does not commute with the 3rd power of r. Same thing with the 9th power of r. T doesn't commute with the 9th power of r because r to the 9th times t is tr cubed, where t times r to the 9th is tr to the 9th. And so since those are not equal to one another, t doesn't commute with r to the 9th, and since these aren't equal to each other, t doesn't commute with r to the 3rd. And so that's really asking an element-by-element commuting question. Right? But it's a different question if I ask whether t commutes with the whole set. Right? The difference is, in the first problem, I'm asking, do I get the same element every time I multiply one of the elements of H on the left or on the right by t? That answer is no, because of this disagreement and that disagreement. But when I zoom out and I look at the whole set H, do I get the same set of elements when I multiply all the elements of H on the left by t as I do when I multiply all the elements of H on the right by t? And that answer is yes. Because sets don't care about ordering of their elements, right? It is the same set for me to list t, tr to the 9th, tr to the 6th, tr cubed, as it is for me to list t, tr cubed, tr6, tr 9th. Right? Sets only care about their members and not about the orderings of their members. And so the right coset ht has those 4 elements. The left coset th has these 4 elements. But every element of one of those sets is also an element of the other, and vice versa. And that means that these 2 sets are in fact equal. th and ht are equal as sets. And it's that equality as sets that defines the definition of a normal subgroup, right? So this would be one of the, in fact, it turns out because T and R generate the dihedral group, it turns out this is a sufficient check to show that, in fact, this H ends up being a normal subgroup of D12. We know that this H is going to commute with every R, every power of R, because it's made of powers of R, and powers of the same element always commute with one another. And now that I've verified that it also commutes with T, and every element of the dihedral group is made up of T's and R's, this verification will show that in fact H commutes with all elements of the dihedral group as a set. The whole set is the same, even if the orders of the elements that we get in that set, orderings I should say, of the elements in that set are different, because T, for example, doesn't commute with every element of this subgroup, but it does commute with the subgroup as sets. And that's the difference. So how this shows up sometimes in the work that I would see a student do, right, is I would ask a question similar to the following. So let's suppose that I asked you in this question to check whether H was a normal subgroup. Is H normal in D12? And for the people who were mixing up these two definitions, what they would often do is they would look at the elements of H, and they would start doing this left multiplication and right multiplication process. And they would turn up, just sort of going down the line, right? They would multiply the identity on both sides and say, well, the identity works, IT is equal to TI. Then they would do the next element, and they would turn up this one disagreement. TR cubed is not equal to TR to the 9th. And then people would stop there and say, T didn't commute with this element R cubed, therefore this subgroup cannot be normal. But that misses the point, that equality needs to happen not element by element. That's a stronger condition. That's a center or a centralizer condition. Right? We don't need that equality to happen element by element. We need it to happen at the level of the whole set. Which means that we really do need to check that even though TR to the 9th showed up here instead of TR cubed, if we keep going, this TR cubed ends up showing up later on in my right coset. And this TR to the 9th ends up showing up later on in my left coset. So the moral of the story is if you're checking to see whether a subgroup is normal, you cannot stop after just checking that one of its elements doesn't commute with something. You have to understand the entire left and right cosets before you can make that determination. So keep these two definitions square in your mind so that you don't end up talking yourself into a corner by trying to insist that your subgroup be central rather than just be normal, which is the weaker condition. Every subgroup of the center of a group is guaranteed to be a normal subgroup, but not every normal subgroup is a subgroup of the center. In fact, just to finish the thought on D12 here for a minute, we saw that R to the power 6 here ended up actually commuting element by element with T, right? TR to the 6th was the same as R to the 6th times T. And because it commutes with T, and it also commutes with all the powers of R, it turns out that R to the 6th does commute with everything in D12. Commutes with every element of D12. So we're actually going to come back to this example a little bit later, because we can show that it's also the only element that commutes with every element of D12. And so the center of the group D12 has the element R to the 6th power in it, because R to the 6th commutes with everything. And of course, it also has the identity. The identity element in any group always commutes with everything as well. And that turns out to be it. So this is the center of D12. So when we get an opportunity to talk more about centers a little bit later on, we're going to use centers of dihedral groups as an example to motivate some of what we'll do next. So now that we've had a chance to talk some about center and use it as an excuse to sort of go into our topic number 7 and talk more about cosets again, I want to talk more about factor groups because I worry a little bit that we didn't really have the time at the end of this semester to let it sink in that factor groups are something that, whether we knew it or not, we're actually already familiar with. We just have to kind of be introduced to the way in which we already know some kinds of factor groups. It's a bit like trying to introduce somebody to the taste of their own tongue, right? You walk around tasting it all day, but we don't know what it tastes like until we think about it, right? So I want to do that by looking at a couple examples of factor groups that I hope we'll be able to latch onto pretty quickly, because we've already seen them in two different guises. One of them is going to take us just back to the beginning of our semester in abstract algebra, but the other example of a factor group that I want to talk about together will actually take us back to pre-calculus maybe or something. I want to link factor groups into a discussion about really geometry or trigonometry if you want to be fancy, but we're not going to use any sines or cosines. It's really just about measurements of angles. So here comes a couple of examples of factor groups that I'm hoping are things that we might already know something about. So how do we start? We're going to start from an abstract algebra perspective by just taking two groups that we don't have to think too hard about their structure. One of them is the additive group of integers. -3, -2, -1, 0 to 1, 2, 3, etc., right? On to infinity on both sides with the operation of addition. And then also the additive group of all real numbers. And of course, it's not up for abstract algebraists to define what the real numbers are. I don't even know if there is an algebraic way to define what the real numbers are. It kind of is. Most of the more satisfying ways to do it rely on the point set topology rather than on algebra. So you do this in a course like real analysis rather than a course like abstract algebra. But let's assume for the moment that we can just get by on our sort of intuitive, conventional, heuristic understanding of what the real numbers are and use addition as the operation on that group as well. So I want to do this by introducing you to two subgroups, a subgroup of the integers and a subgroup of the real numbers. So here's a subgroup, 6z. So this is the subgroup of the integers, additive group of integers, that consists of all the multiples of 6. Right? So -18, -12, -6, 0, 6, 12, 18, 24, and so on. Right? That's a subgroup. You can check that it satisfies all four of the subgroup properties, or we can just apply a subgroup test. For example, if I subtract any two elements of this set, when I subtract two multiples of 6, the result is always again a multiple of 6. Therefore, the one-step subgroup test guarantees that the multiples of 6 form a subgroup of the group of integers. So that's the subgroup I want to think about in Z. What about in R? In R, I have a funnier subgroup in mind. This is the subgroup of all integer multiples of 2 pi. So this subgroup is going to have elements like -24 pi, -22 pi, -12 pi, -4 pi, -2 pi, 0, 2 pi, 4 pi, 12 pi, 100 pi, 100 million pi. All of those even integer multiples of pi. Those, again, form a subgroup of the real numbers. If I subtract any two integer multiples of 2 pi, the result is again going to be an integer multiple of 2 pi. In fact, both of these subgroup examples are examples of cyclic subgroups in their respective groups. Well, almost. So, no, I guess it is cyclic subgroups, right? This is the subgroup that I get by adding 6 to itself any integer number of times. This is a subgroup that I get by adding 2 pi to itself any integer multiples of times. Right? So both of these are cyclic subgroups of their respective parent groups. And so the question that I want to kind of wrestle with together is, let me pose it a couple of different ways. First of all, I want to talk about index. What is the index of each subgroup? And so index is a definition that I think some people have been asking me about this week, so I just want to take an opportunity to talk about it now just to clear it up. When we say the index of a subgroup, what we really mean is how many cosets, how many distinct cosets does it have? Right? And so depending on if you have a finite group or an infinite group, we may have to do more or less work. If we have a finite group, we can just use Lagrange's theorem. Finite group, use Lagrange. Because Lagrange's theorem is going to tell me that the order of my parent group has as one of its factors the order of the subgroup, H. And the cofactor that goes along with it is what we call the index of that subgroup. So this missing factor here, which we'll denote with brackets and a colon, this is called the index of H in G. Index of H in G. And so if we have a finite group, we can use Lagrange's theorem just to compute the index to be the order of the bigger group divided by the order of its subgroup. Done. In the row by column metaphor that I keep using, G is the whole table of elements. The order of H, the number of elements in my subgroup, is the number of columns in my table, and then the index is the number of rows in my table. So that's one question I want to ask. And the second question is, what can we say, if anything, about the structure? What's the structure of the factor group? What is the factor group elements? What are those elements really doing? of the factor group. And by factor group, of course, I mean G mod H, right? So those are the two questions that I want to kind of explore together. Let's start with the additive group of integers and using as my subgroup the multiples of 6. So here's how, let's go to the rows by columns metaphor, because I use that one a lot. And it's got some limitations, but I also think it's a really powerful way to gain a first understanding of how factor groups work. So I'm just going to actually open a spreadsheet window here. Never knew you could use Excel to do abstract algebra, but I think we've got an opportunity here just to, I just want to do less computation if I don't have to do more. So let's bring that up onto my screen here. Uh-oh, that's not working the way that I want it to. All right, we'll just do it that way for right now. All right, so in my group Z, I've got a subgroup that we're calling H, and it's made up of all the multiples of 6. So let me just sort of put in some multiples of 6. Try to do that as quickly as I can here. And then we'll just remind ourselves that there's really a dot, dot, dot on both ends of this. Right, so here is my subgroup. Just try and make sure it all gets on the screen here. And as I'm accustomed to doing, let's just kind of shade it a certain color. Right, so here's my subgroup inside of Z. Because it's a subgroup, it's going to be closed under the operation of my group. My operation is addition, right? So if I pick any one of these numbers and I add it to any other of these numbers, I'm going to get another one of these numbers. So the question now is, how do I find a non-trivial coset of this subgroup? Non-trivial coset must contain an element, must contain new elements. Let's say it this way. Must have a new element. And what I mean by that is the best way to understand how to get a non-trivial coset is to pick an element which doesn't belong to my subgroup in the beginning. I don't, for example, see the number 1 anywhere in this first row. And so from the point of view of cosets, 0 and 1 are going to reside in different cosets. But then 1 is going to reside in a coset with a bunch of other stuff. And the key here, right, is that 1 is in the same coset as x if and only if the difference between x and 1, so x minus 1, is a multiple, or is an element of h. Okay, so this is the principle that I want us to kind of latch onto when it comes to thinking about cosets. Two elements are in the same coset of h if the only difference between those two elements, that difference is an element of the original subgroup, h. So what we're doing when we're thinking about factor groups is we're trying to blind ourselves to any differences between elements in my group when those differences belong to my designated subgroup, my normal subgroup H. Right? So any two elements which differ by a multiple of 6, so I'm going to clarify that here, x minus 1 is a multiple of 6, right? Any two numbers which differ, integers which differ by a multiple of 6, will be in the same coset as one another. And so 1 will be in the same coset as 7. Why? Because 7 minus 1 is an element of h, is a multiple of 6. And for that same reason, 13 is also an element of the same coset as 1, because 13 minus 1 is the same, is a multiple of 6, and so it belongs to the original subgroup H. So you can maybe kind of see what pattern is emerging here, right? We can get all of my different elements of the same coset. So to go from the same coset to itself, we're adding multiples of 6 to 1, or to 7, or to -5, or whatever. That takes me to different elements in the same coset. And to get this coset from my original coset, what I'm really doing here is I'm just taking this 1 and I'm adding it to H. So the name that we might give to this, the name that we might give to this coset is 1 plus H. So this coset we'll call 1 plus H. And because it's 1 plus H, that means, this is why I'm using Excel for this, I can just take 1 plus and then choose that cell that's above there, just copy and paste. Whoops. Uh-oh. Try that again. Copy and paste. There we go. So here are the elements in the coset 1 plus h. And again, anytime we're talking about cosets, what we notice is that these two cosets don't overlap one another at all. There's no elements that these two share in common. Different cosets of the same subgroup are either completely disjoint, as these two are, or they are exactly the same. They overlap entirely. So 1 plus h has nothing in common with h because it has even one thing that the other one doesn't. And so as you might expect, the next subgroup available here might be 2 plus h. So that if I, let me copy this down here. So what's 2 plus h look like? Well, all I have to do, again, here is just take my 2 and add it to the element of h. So negative 18 plus 2 is negative 16. Negative 10, negative 4. And then all the elements over here, which I get by adding 2 to a multiple of 6, right? And so if you're wanting to continue this pattern, right, we would go to here, and then we would go to 6, right? And then I would just take this and copy this down. Copy. Whoops, what just happened? What did I do? Copy and paste. And then I would also want to paste this stuff. Paste it over here. Okay, something weird is going on here. I'm screwing something up. Yeah, that's not what I want. All right, sorry. I'm getting a little mixed around here. So what I want to do is I want to add this to the third row. There we go. Copy that. Paste it there. Okay, now this looks like it's working the way that I expect it to. Probably shouldn't have done this with Excel. Probably should have just written the silly numbers where they belong. But whatever. Okay. So I keep doing this process, and every time I do, I get another coset of the original subgroup H. But what do you notice? Once we get to 6 plus H, we actually end up getting the very same elements that we started with on this row, right? Negative 12, negative 6, 0. These are all just, again, the multiples of 6. And so what I ended up with here is just the original subgroup H again. So rather than listing it as a new row, we'll just forget about it. We'll hide it. And here then are my 6 non-trivial cosets of H, if you like. H, 1 plus H, 2 plus H, 3 plus H, 4 plus H, and 5 plus H. So, there we go. All right. So there are my cosets for this particular subgroup. So let's come back to the question that I posed here. First of all, what is the index of this subgroup? It's the same as the number of rows that we had in this table. So here's my table again. And so the index in the group of integers, the index of the multiples of 6 is the number of rows that I had in my table, right? Here's one element, here's another element, here's a third, a fourth, a fifth, a sixth, right? So here were each of the individual cosets of H. There were 6 of them, and so the index of this subgroup is equal to 6. Let me shrink that a little bit there. Okay, and so then the question is, what can we say about the factor group? The factor group is the group which we get by considering each one of these cosets to be an element rather than made up of different elements, right? And so my factor group, Z mod 6Z, has as its elements H, 1 plus H, 2 plus H, 3 plus H, 4 plus H, and 5 plus H, right? So those are the elements in my factor group, Z mod 6Z. So my factor group is a group of 6 elements. That's that. The index, again, tells me the order of the factor group. is a group of order 6. Well, what is its structure? So to figure out its structure, I'm going to claim, and then argue for why, this group is actually a cyclic group. So I'm going to claim that it's cyclic. And I'm going to claim that it's generated by 1 plus h. 1 plus h. So why should I expect that 1 plus h, this element, right? It's a coset of the original group of integers, but it's an element in my factor group. Why is it reasonable to expect that 1 plus h is going to generate my entire factor group? Well, what do I get when I add it to itself once? 1 plus h plus 1 plus h. Well, here's the beauty. In order to add these together, I get to use the fact that h is a normal subgroup of my original group. I know it's a normal subgroup because my original group was an abelian group. Right? The group of integers with addition, that's abelian. And so all of its subgroups are normal. So h plus 1, element by element, must be the same as 1 plus h. Right? So I can turn h plus 1 around into 1 plus h. And the benefit of doing that is that now I can add these 1's together and get the element, the integer, 2, right? 1 plus 1 is going to give me 2. And my h's, if I add any element of the subgroup h to any other element of the subgroup h, the result, by closure, is always going to be an element of the subgroup h. And so I end up with 2 plus h as the sum. So 1 plus h added to itself is going to give me 2 plus h. And as you might expect, if I add 1 plus h to itself 3 times, I'm going to get 3 plus h. If I do it 4 times, I'm going to get 4 plus h. If I do it 5 times, I'm going to get 5 plus h. And when I do it the 6th time, 1 plus h added to itself 6 times. So all those 1's are going to get added together. And then I'm going to get a plus h at the end. Right? But once I've added all these 1's together, as an integer, I get 6. But 6 is already an element of my original subgroup h. And so 6 plus h, again by closure, is equal to the same thing as 0 plus h, because 6 and 0 differ by an element of h, by a multiple 6. And so once I have added 1 plus h to itself 6 times, I come back around to h, which is the same thing as the identity element in the factor group. So that must mean that z mod 6c is isomorphic. It's really, quote unquote, the cyclic group of order 6 that we otherwise know in our course as z mod 6. So this gives us kind of a viewpoint of what a factor group is doing. I'm going to try to make a little visual here that I hope is going to work. I'm going to go back to our clock visual one more time because I end up using this visual just endlessly when we talk about modular arithmetic. This is why modular arithmetic works, and it's why we call a factor group a mod, a G mod H, right? Because we're making the analogy to modular arithmetic. So it's like taking my integers and arranging them all around the outside of a clock. So let me start with 0, right? And then I've got 1, and then I've got 2, I've got 3, I've got 4, I've got 5. But then once I get to 6, I have come back to the same position on the clock as I started. And so 0 and 6 end up being the same. If I keep going, 7 is going to end up in the same position as 1. 8 is going to end up in the same place as 2. 9 and 3, 10 and 4, 11 and 5. And then 12 is going to end up in the same spot as 0 and 6 did. 13, 14, 15, 16, 17, 18. And if I went backwards around the clock, -1 would end up in the same spot as 5, -2 in the same place as 4, and so on. -5, -6, and so on and so on. So there's a way in which we're kind of just taking the group Z, all infinitely many elements of the group Z, and we're just wrapping them around a 6-hour clock. And when we do that, we now lose the ability to tell the difference on the clock face between the number 12 and the number -6. or to tell the difference on the clock face between 9 and -3, or between 13 and 7. Right? Because those differences are all multiples of 6, they occupy the same position on a 6-hour clock. And so the factor group is the group that we get by just thinking of each of these whole sets as just being a single element unto themselves. Right? So everything which is in my top of the clock position is a single element. Everything that's in this position is a single element. Everything that's here is one element, one element, one element. And these 6 elements, which also add together in the same way that Z mod 6 does, the ordinary Z mod 6 around a clock, these 6 elements are my factor group that I get. So I started with infinitely many elements, but once I consider every 6th one of them to be the same, we've wrapped them around a 6-hour clock and gotten the finite group, Z mod 6. So that's an example of a factor group that we already knew. We knew it back in week 3 or 4 of the course, but we didn't call it out back then as a factor group, even though that's what it is. And there are a number of abstract algebra authors and professors and people who practice abstract algebra that will never write Z subscript 6 to mean the cyclic group of order 6. They'll actually write it as a quotient, Z mod 6Z, every time. So these two really mean exactly the same thing. This just helps us to understand how this arises as a quotient of the additive group of integers. All right, as long as I have this circle on the screen, let's do one more example. This is the other one that I have on the screen here of a factor group that we secretly already know about. And this one comes from geometry, or pre-calculus, if you like. Okay. So this is what I get if I take the whole real line. And of course, the whole real line is an infinitely long. We usually write it out as though it looks like a straight line, right? So here is my real number line. It goes in both directions, right? Its identity element with respect to addition is 0. And then inside of that real number line, I'm singling out a cyclic subgroup generated by 2 pi. And so H is going to contain 0. It's going to contain 2 pi. It's going to contain 4 pi. It's going to contain 6 pi. It's going to contain negative 2 pi, negative 4 pi, and so on. Okay, H. So how many different cosets are we going to get if I take the elements of H and I add an arbitrary real number to them? Well, the real numbers are thick, right? They're dense in themselves. And so there's actually infinitely many different real numbers that I could add to minus 2 pi, just in between 0 and minus 2 pi, for example. So there's actually infinitely many cosets for this H inside of the real numbers. So this is a subgroup of infinite index. So there's infinitely many elements in my factor group. So my factor group is going to be an infinite group. But how do I understand what this factor group actually is? So if I pick an element in my factor group, I'm going to call it theta. If theta belongs to the factor group R mod H. Well, remember, in the factor group, the elements are cosets of H. And so rather than writing it as theta, I'm going to write it as theta plus H. And then remind myself that H is really the set of multiples of 2 pi, so 2 pi z. So really, my elements look like theta plus 2 pi z. So then, what are we talking about here? If you give me a number like, I don't know, pi over 3. So there's an example of an element of the real numbers. But in the coset of pi over 3, so pi over 3 is going to belong to the coset pi over 3 plus 2 pi z. And so it's going to be in the same coset as any other real number which differs from pi over 3 by an integer multiple of 2 pi. So if I want another element in my same coset, I just want to add 2 pi to pi over 3. If I add 2 pi to pi over 3, I'm going to get 7 pi over 3. So plus 2 pi, 7 pi over 3. And if I add 2 pi again, I'm going to get 13 pi over 3. If I subtract 2 pi instead of adding, I'm going to get negative 5 pi over 3. minus 5 pi over 3. If I subtract one more time, I'm going to get negative 11 pi over 3. And so on and so on. So, the coset of pi over 3 contains all of those angles. Minus 11 pi over 3, minus 5 pi over 3, pi over 3, 7 pi over 3, 13 pi over 3, and so on and so on. So, my question to you is, what do all of those angles have in common? All of those angles occupy the same position on the unit circle. Right? So, taking r and taking its quotient, its factor group, by 2 pi z, really has the effect of wrapping the real line around the unit circle. So on my unit circle, usually we put the angle 0 over here at the right-hand position, right? And then pi over 3 is going to be somewhere like here. That's my 60-degree angle, right? There's my angle of pi over 3. But that angle of pi over 3 on the unit circle is the same as the angle that we would get by going an additional 2 pi radians around and getting myself to 7 pi over 3. So pi over 3 is the same as 7 pi over 3 on the unit circle. It's the same as 11 pi over, or 13 pi over 3 on the unit circle. It's the same as minus 5 pi over 3 on the unit circle, and so on. All of those real numbers are different. So when I'm thinking of them as real numbers, those are all different real numbers. But as soon as I consider 0 to be the same thing as 2 pi, which is what we do when we're talking about angles on a unit circle, when 0 and 2 pi are no longer different, that means that pi over 3 and 7 pi over 3 are no longer different. And 13 pi over 3 are no longer different. And minus 5 pi over 3 are no longer different. That is the idea of a factor group. We decide that the differences that we don't want to matter no longer matter. And we can no longer tell the difference between two elements of my group when that difference is a member of the subgroup that we're erasing. So taking a factor group is a bit like erasing a subgroup. Taking the subgroup and saying, I'm not going to care any longer about differences between elements in my group as long as the differences can be accounted for by this subgroup. When the multiples of 2 pi no longer matter, then pi over 3 becomes the same thing as 7 pi over 3, for example. When the multiples of 6 no longer matter, then when the multiples of 6 no longer matter, then 1 becomes the same thing as 7, and 4 becomes the same thing as 22, right? Taking a factor group is about erasing differences, erasing a specific subgroup worth of differences, right? And saying that the elements of those subgroup we want no longer to be visible, right? And so we're sort of collapsing them away. All those differences become trivial, and they become trivial because we can no longer tell them apart from the identity element. And therefore, any other elements of my group which differ by an element of H, we can no longer tell the difference between that and them differing by the identity element, in other words, not differing at all. So once the multiples of 6 are all equal to one another, then everything which is congruent to anything else mod 6 becomes equal to one another as well. So this is where I have to wrap up the first segment of our live stream for today. I do want to come back later on this evening to talk some more about homomorphism counting and the nifty center theorem. So join me a little bit later on this evening. I'll send an announcement via Slack for when you can do that live, and I hope to see you then.